Well, hello, everybody. My name is Chris Barkin. I want to welcome you to today's virtual William W. Hay Railroad Engineering Seminar. Before I introduce our speaker, I'd like to take care of a couple of short housekeeping items. First of all, if you have questions, please use the Q&A feature in your Zoom app, not the chat. We'll be looking at the Q&A section for the questions, and we'll discuss those after the presentation is over. Also, if you are seeking PDH credits for your participation today, those are available. To obtain them, please follow the prompts after the registration on the Hay Seminar page. Also, a link to these instructions is in the chat, or you can contact us directly via email at hayseminar@illinois.edu. So the William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. On behalf of all of us, we thank the Association of American Railroads, BNSF Railway, CN Railway, Hanson Professional Services, and the National University Rail Center of Excellence for their ongoing support of Railtech. It is greatly appreciated by those of us here on campus, as well as of those participating via the internet. I want to welcome more than 200 people who have registered for this seminar today. They hail from 15 different countries on 6 different continents. This list of attendees includes freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers and suppliers, and many others. We are very pleased that you could join us today. So, the presentation today is going to, as I've said, is going to be by Yuanchen Zeng, and he's going to be talking about railway, track, and rolling stock. These are among the most critical assets in rail transportation from both an operational, safety, and cost standpoint. Efficient inspection, assessment, and maintenance is essential. Onboard and wayside inspection technologies enable network-scale condition monitoring without disrupting operations, while predictive maintenance approaches offer the potential to further improve safety and reduce life cycle costs. This presentation introduces recent research on inspection, assessment, and maintenance strategies that leverage vehicle-track interaction data. I'm very pleased to be introducing our speaker today. Dr. Yuanchen Zeng is an incoming assistant professor in Railtech here in the Granger College of Engineering at the University of Illinois, Urbana-Champaign. He will be joining us this summer. He's currently a postdoctoral researcher at Delft University of Technology, and his research focuses on non-contact sensing, structural health monitoring, intelligent assessment, and predictive maintenance of rail infrastructure and rolling stock. He earned a PhD in railway engineering from Delft University and also a PhD in vehicle operation engineering from Southwest Jiaotong University. As many of you know, these are 2 of the top railway programs in the world, and so we're exceedingly pleased that he's chosen to join us here in Railtech. And as part of his previous work, he's contributed to more than 10 projects in Europe and China. So I'll now turn the virtual podium over to my colleague, Dr. Yuanchen Zeng, who will present non-intrusive inspection and predictive maintenance of railway tracks and vehicles leveraging their interaction. Dr. Zeng? I think you're on mute.
Yes. Thank you, Chris, for the very kind introduction. And I believe you can hear me well.
Yep.
Great. And I'd like also to extend my thanks to you, to Riley, and to the Railtech team for the invitation and for organizing this seminar. And actually, I've been following the Hay Seminar in the past and learned a lot about interesting research and a lot of practical insight as well. So it's a really great seminar series. And it's a great honor for me today to be here virtually and to have this opportunity to share my research and also my vision in this topic. So the presentation topic would be non-intrusive inspection and predictive maintenance of railway tracks and vehicles leveraging their interaction. So as Chris mentioned, I'm currently a postdoc researcher at TU Delft, and I will be joining the University of Illinois Urbana-Champaign as assistant professor this summer. I had a PhD in railway engineering from TU Delft and also 1 PhD from Southwest Jiaotong University in China. I completed my undergraduate studies at Zhejiang University, which is also in China. But before I dive into my research work, I'd like to briefly introduce the two universities where my research was carried out. So I'll start with Southwest Jiaotong University, which is also the university where I started my railway research. It is located in Chengdu, China, apparently in the southwest part of China by its name. And the university actually has a railway connection to the network of Chinese railway, including a turntable that allows locomotive or wagons to rotate and switch to the tracks. But this connection is not for passenger service, but they are used to allow trains to enter the campus for testing. This is because the university is the home for the world's highest speed roller rig. It can run up to 600 kilometers, which is roughly 73 miles per hour. And the rollers can not only drive the train wheels to run at high speed, but can also generate geometric and dynamic excitations to the train. There are also a variety of other lab test facilities and test beds, roller rigs, all kinds of facilities at the university. So it is really a leading hub for railway research and education, both in China and also worldwide. And it has a long-term partnership with the railroad industry in China. So actually, Southwest Jiaotong University made significant contribution to the development of China's railway system, including the high-speed network. The next is where I am currently now, TU Delft, in the Netherlands. So we have a beautiful campus, and this is our ski resort. But actually not, it is only became a ski resort maybe once after a few years when we really have enough snow. In reality, it is our campus library. And here is our faculty, so the Faculty of Civil Engineering and Geoscience. And right in front of our building, there is a tram line. And actually, it's already been many years of delay, but this year we are finally expecting trams to start operating through our campus by the end of this year, hopefully. So TU Delft also has a long history and very influential impact in railway engineering. For example, Kalkar's theory in railroad rolling contact mechanics, developed by Professor Kalkar, is a truly foundational contribution to the field and is widely used worldwide. TU Delft also contributed to widely used reference books in the field, such as the book Modern Railway Track. On top of that, we also have advanced testing and monitoring technologies and facilities to support both fundamental and practical research. So let me get my pointer. So here on top, you can see the vehicle track interaction test rig. And here it is our CTO measurement wagon. And you will see both of them later in my presentation. And at TU Delft, I had the fortune to be involved in many projects funded by the European Union, the Dutch Ministry, and the Dutch Rail Infrastructure Manager, ProRail. One project I'd like to highlight here is the Europe's Rail flagship project, I Am for Rail. It involves dozens of partners across Europe and a grant of tens of millions of euros. And the goal of I Am for Rail is to bring together all players, stakeholders, researchers to try to build a holistic and integrated approach to railway asset management. So we are very glad to be part of this great effort. So I hope that gives a bit brief overview of my background, where I came from, what I did overall. And now I will briefly outline the structure of my talk today. So I will start with the motivation of my research, then move on to three core topics: inspection, assessment, and maintenance. And finally, I will conclude with some key takeaways. So actually, like Europe's railway systems, American railroads are also among the oldest in the world. Railroads used to play a larger presence in the States, but even after a significant reduction in network length, it is still the largest in the world, with about 140,000 route miles. Railroads played a key role in the economy of the country with over 1.6 million rail cars moving across this vast network. And the network is actually managed and operated by many, many different railroad companies, ranging from Class 1 railroads to hundreds of regional and short line railroads. On top of that, operating conditions also vary significantly. For example, axle can differ substantially with relatively light passenger traffic and much, much heavier freight traffic, and they share the same infrastructure. And to properly and effectively manage all these assets, both the rolling stock and infrastructure, inspection and monitoring are playing an essential role here because they help us understand the conditions and also help us to make better plan and prioritize the maintenance. So here is one way I'm trying to classify different inspection and monitoring technologies. So we can look at it actually from two perspectives. So in the horizontal axis, the sensor can be mounted either on the vehicle or rolling stock or on the infrastructure or the railway tracks. And the sensors or measurement can be used to assess either the track here on top or assess the rolling stock or the vehicle right in the bottom. So these give us 4 categories of technology, and we can use sensors on the wayside to directly measure the track components, or we can use sensors on board of the train to monitor that particular wagon or the train component. But you can imagine if we want to apply this to the entire large-scale asset we have in the country, it would be very expensive. But fortunately, railroad offer us this guided relative motion between vehicle and track. This is a powerful opportunity that allow us to use, for example, sensors on board of moving train to inspect the railway track at a larger scale. Likewise, we can also use sensors at the wayside to inspect all the passing rolling stock. So this is really a very powerful and very important opportunity for us to do truly non-intrusive, continuous, and large-scale inspection. But this concept is not new. It has been developed for decades, and many inspection technologies have been developed, applied, and even get standardized, such as track geometry and vision-based method. At the same time, there's always a need to get more information, that is we haven't been able to measure yet, that is complementary to what we already have, so that we can get better detection, more accurate, and also potentially earlier stage detection. And these information are very important because we can make use of them to predict the remaining useful life of our assets and to also help us to do predictive maintenance more effectively. And the effectiveness of doing this and the benefits is obvious. We will get further improved safety, reduced accidents, including derailment, and also we can increase the availability and improve the service quality of the railway assets. And also for railroads, it is great to have both improve safety and also reduce the cost so that we can also get more cost-effective maintenance decisions made. So this is actually the motivation for my research on 3 major topics, actually. First is non-intrusive vibration-based inspection. Then is condition assessment, leveraging vehicle track interaction, followed by predictive maintenance, considering life cycle degradation and cost. So here at this point, vibration comes into our picture, and I'd like to briefly explain why it is here. So this is a simplified representation of a degradation over time. And we have degradation over time, the condition drops, while at the same time, the cost to repair or recover the condition of the asset will also increase as the degradation gets more and more severe. And different inspection or monitoring technologies may have different sensitivities to detect defects at different stages. And it's, in general, vibration-based methods have stronger potential to detect early-stage anomalies, often before they develop into more severe, more problematic problem like that is really visible by geometry or even by visual inspection. So it is because of the power of the vibration to do early detection, it comes into the picture of my research. So in the following part of my presentation, I will show how my past research tries to achieve these objectives. So the first part is, how can we achieve non-intrusive vibration-based inspection of railway tracks? So one approach is actually we can measure the vibrations of the vehicle component. It can be on the car body, it can also be on the bogie or the truck frame, or on the axle box. For example, here we have the accelerometers on the axle box, and we can detect rail surface defects that give rise to a wheel rail impact. So here you can see the acceleration signal on the axle box, and you can see some localized feature that can detect these kind of surface defects on the rail. And we further combine this acceleration measurement with, for example, GPS data, we can further locate these defects along the track. So this is the result we obtained from a measurement campaign we did on the iron ore line in Sweden. An interesting extension of this idea is to do ground sensing. For example, we can use smartphones, which also has an accelerometer inside. We can use smartphones inside passenger trains to measure vibration signals during normal vibration. And from this research, we find also nice correlation between acceleration measured by smartphones with the track geometry measurement using specialized inspection car. However, in general, these methods, either measuring axle box acceleration or vehicle vibration or car body vibration, it is essentially an indirect way of monitoring track condition through service response, vehicle responses. So railway tracks are actually complex, multi-layered system, and train vibrations are influenced by many variables. We have the different track layers. We have also the suspension system of the vehicle itself. As a result, such techniques face significant uncertainties and become less sensitive to problems in deeper layers of the track structure. So then we have a question, is there a more direct way to do this? For this, we introduced a technology called laser Doppler vibrometer, by short LDV. So this technology works based on the same principle to something we are probably more familiar with, a radar speed gun. So a radar gun emits a microwave towards something that is moving relatively fast, like a car, and then the wave got reflected by the car back to the device. And suppose that the car is moving at the speed of v, and the emitted wave has a frequency of f and the wavelength of lambda, and due to the well-known Doppler effect, the received wave by the device will have a shift in the frequency. So that is a so-called Doppler frequency shift, delta f here. And this frequency shift is proportional to the moving speed of the target, which means we can measure the speed of the target by measuring this Doppler frequency shift. And LDV actually works on the same principle, but instead of using microwaves, it uses laser light. So the LDV now sends a laser beam to a target that is vibrating, and then this light is also reflected back to the device, back to LDV, and then it will also give you a shift in frequency. And this frequency actually follows the same equation we're showing here, and based on which the LDV can measure the vibration speed or vibration velocity of the target, which is essentially the time derivative of the vibration displacement. Compared to a radar speed gun, LDV uses laser light, which has a much shorter wavelength and a much higher frequency. So these allow us to detect much smaller vibrations or smaller movement, for example, a few micrometers per second. LDV can also measure very broad frequency bands from 0 to up to several megahertz. And at the same time, the laser has a much smaller measurement footprint, which also can achieve very high spatial resolution. But I have to also mention that these capabilities, this high sensitivity, do not come simply replacing microwaves with lasers. Achieving this level of sensitivity requires very sophisticated design in optical part, electronic part, and also in the signal processing part. So actually, this technology has been developed and refined since 1960s, and they continue to evolve today. The biggest advantage of LDV here is that it measures vibration without the need for contact. This means that there's no need to attach sensors to the target. It can allow us to access places that are difficult to reach. For example, a surface is a working surface that is not possible to attach anything on it. In addition, it also provides much or greater flexibility to adjust the position of the measurement location by simply guiding the laser beam. So LDV is widely used in stationary setups where the laser beams is guided typically by a mirror or a scanner to measure multiple locations on a structure. So this is an example where we can see a LDV is mounted on the tripod and its laser beam is guided to measure a dense grade of points of a structure. And all these measurements can support, for example, the identification of the mode parameters, including mode shapes of the structure. But in our research, we use LDV in a different way. We mounted LDV on a moving train and with a laser beam directed right on top of track structure. So that as the train moves along the track, the laser continuously scans the railway track and measures the vibration excited by the same train. So the moving train here serves as the excitation sources, and it also carries LDV to capture the vibration response that is excited by the moving vehicle. However, this approach sounds great, but it also introduces a lot of challenges. So the first one is because of the sensing nature of the LDV. So because LDV essentially measures vibration relative to the sensor head. So that in our application, because the sensor is mounted on the moving train, which is also vibrating, so the vibration of the laser head will also introduce an additional frequency shift into the measurement. So if you still remember this equation of the Doppler frequency shift, now we have additional speed component or vibration velocity component, which comes from the vibration of the laser head on the moving train. Therefore, we not only measure the track vibration velocity, but also in the raw signal, we have also the vibration of the laser head itself, which must be taken into account. Secondly, and also a very serious challenge, is the so-called laser speckle noise. It actually comes from the backscattering of a laser light or a coherent light from an optically rough surface. And here the railway track is an optically rough surface. And it comes from a pattern that is bright and dark, but with random distribution. I can show an example from our daily life or from the nature to help visualize a bit what is a bright and dark pattern that created in terms of light. So here I have the sunlight reflected by a water surface. And also there is wind that is blowing. So the surface is not still, it actually moves or dances. So that you can see that when the wind disturbs the waves, the water surface, we can see the fluctuating patterns, bright and dark, but fluctuating. So this is intuitively similar to the changing speckle patterns observed by a train-borne LDV. Although in physics, they are not exactly the same, I would say. And it actually, this change in speckle patterns that generate the so-called speckle noise, and which will also give additional component in the Doppler frequency shift. So we have the laser head vibration as a disturbance. We have also this changing speckle pattern, which will also give additional frequency shift, which is even worse because it's kind of very random and very unpredictable. And if you look at the LDV signal, speckle noise will appear as random spikes or dropouts in the signal. So as those labeled here in the plot by the right part. And it is typically a non-Gaussian noise, and it is broadband in frequency. It can affect a very wide range of frequencies. And it is surface and speed dependent. So here on the top, you can see that when we measure, when the scanning speed increases from 0.5 to 20 kilometers per hour, the noise level also becomes more and more severe. So it happens more and more. And we have also the comparison in measurement between asphalt sample from a steel sample. We can also see the noise level is much higher on a surface that is much rougher, like an asphalt. So here, the speckle noise, along with laser head vibration, can significantly degrade the quality of raw tremor LDV signals. Therefore, we need some solution. And we developed a signal processing pipeline that's to try to address all these challenges. So first, for the LDV vibration, the sensor head vibration, we installed accelerometers also on the LDV sensor to measure its vibration. And then we subtract the sensor vibration from the raw LDV signal as a compensation or a cancellation. So this is really important to remove this component so that we can extract the target vibration purely. And for the speckle noise, we developed tailored despeckling algorithm that is designed based on the property of the speckle noise. And the general idea is to first distinguish the data points that is more affected by speckle noise in the time domain, and also considering their frequency features. And then we try to reconstruct the signal by following the vibration trend. And together, these approaches can significantly improve the quality of the LDV signal measured from the moving train. So we have done a lot of validation by doing simulations, but also laboratory tests. But here I want to show only our field validation in the field. We implemented this tremor LDV setup on the CTO measurement wagon, which I showed at the beginning of the presentation. And this is when the train passes Delft campus station, which is not far from our campus. And this is the yellow train that is the CTO measurement wagon. And we have the LDV installed on the train. So you can see the LDV. You can also see the accelerometers, which I mentioned is for the compensation purposes. We have also the real-time signal shown here, which is very noisy because of the speckle noise mostly. Here I show you that we are scanning the rail using the laser, and also here at a higher speed. And I mentioned there is a flexibility to change the location of the laser. So here I'm scanning the cross ties and also at higher speed. And to validate the signal processing method, we conducted simultaneous wayside measurement as the CTO train passed. And we compare the LDV signal with track-mounted accelerometers installed on several cross ties. So here are some representative results after applying the compensation and despeckling method. We can see there's a good match, good agreement between the LDV signal after processing with the wayside measurement from the sensor on that particular cross tie. So this demonstrates that the tremor LDV can capture track vibration well under rail operating conditions. And there's also one thing that is interesting to note, that the match happens mostly well only when the laser on that target, which definitely makes sense because you only measure that target when the laser is on it. So okay, now we have a new field-proven measurement tool that can directly measure railway track vibration on board. So that's great. And the following question is, how can we use the measurement to assess the dynamic properties of the track structure? There are also a couple of challenges. I will just quickly go through some of them. So first, it is challenging to analyze this because of the non-stationary and unknown excitation from the vehicle-track interaction. Because here we are relying on the operational train load. And the train speed also plays a big role here because the speed affects the level of excitation, the noise level as well, and also how long you can measure per piece of track. And we have also the challenge of the laser positioning, because there are cases the laser is not hitting the intended location, which should be identified and excluded. To achieve this, or to address these challenges, we need information not just from the LDV. So that's why we developed this multi-sensor framework. So we have LDV on the moving train, but we have also accelerometers on the vehicle to measure how the vehicle vibrates simultaneously. We use also GPS, we use also a video camera to record the speed profile and also the laser spot position along the track. And these signals need to be well synchronized and combined so that we can get simultaneous measurement of the train and track vibrations with speed and laser position information. While actually doing this will also give us a new challenge actually, that is, we have to process large volumes of multi-format data. So in our measurement, we can generate hundreds of gigabytes of data in a few hours. So that's why we first need to work on this processing of a large data set. So here instead of using the traditional approaches, rely on manually engineered features and thresholding, we developed an unsupervised representation learning method to process the raw data. And it automatically learns features that can help us distinguish between valid measurement and invalid measurement. And on top of this, we developed two indicators to help us understand the track conditions. And they are calculated from the train and track vibrations. So one is for indicating real surface condition, and the other is for indicating track support condition. So here I show you an example where we have a piece of measurement where we have three locations with the first indicator shows peaks, which means that the surface is not good, and actually it is because the wheels. And among one of the three locations, we have also a large track support indicator that shows the peaks. That basically means the track support condition is also not good at that location. This means at this location, there is a coexistence of rail surface problem and track support problems. And we verify these findings by visual inspection and also by track geometry measurement at short wavelengths. And with these two indicators, we are able to understand the type of anomalies and also their possible connections. So this gives also more interpretability of the assessment results. Another approach that can combine vehicle and track vibration is to estimate the so-called load-response relationship. So the idea is that while the LDV captures the track response here, we use also the vibration measured by the vehicle to identify or to approximate the dynamic train load applied to the track. Then we can normalize the response measured by the LDV by this loading information so that we can get a transfer function, or we call it load-response relationship, which is a representative of the track dynamic properties. This is actually very similar to traditionally dynamic stiffness testing using impact hammer. So we have an instrumented hammer that gives impact on the track structure, and at the same time, we measure the response using sensors on the track components. We can also get a transfer function out of this signal, which is following the same or similar representation. And here we can notice that this impact testing is usually done under unloaded and localized condition. Well, here what we want to do is fully on board, it's loaded and continuous. And we also validate this approach, and I will show you here our validation in the V-track test rig of TU Delft. So here on the left, you can see the LDV is mounted on the test rig. We use a mirror to guide the laser onto the track structure so that when the vehicle is moving, the laser scans the track just as what we saw in the field test video. So this is how the test rig is running, but now it is running at lower speed. And it can also run at higher speed. Okay, so when LDV scans each track segment, we can estimate a load-response relationship from the LDV and accelerometer measurement. This is shown by the black curve here. It is a function of frequency f, which represents the load and the response or input and output relationship. We also did hammer tests on the same track segment, so we also get such a transfer function, which is by these colored curves. So overall, we can see a good agreement between onboard and trackside, especially in terms of the overall shape of the transfer functions and also the main resonance frequencies. We can also see some differences, like the frequency resolution from the onboard measurement. The black one is worse than the wayside one, which actually is expected because we have a much shorter signal from the onboard measurement. But this limitation can be compensated by the ability of the onboard approach to do frequent and continuous measurement. And such a representation is very useful for asset management because it is a very reachful and comprehensive representation of the dynamic properties. So at some frequencies, it indicates some the condition of maybe the track support, the ballast condition, while at some other frequencies, it may indicate the real fastening problems. So this really makes measurement, the estimation result very informative. And also because of the normalization by the loading information, so this result is also more comparable across different locations so that it makes continuous inspection and assessment possible. Okay, I'd like also to mention a very fun historical note here is that Doppler effect in the history was actually first time experimentally verified in the Netherlands and actually using a train track systems. And today we're using a sensoring technology named by this theory to inspect railway tracks from moving trains. So I believe it is very interesting to remark or to note this connection with the history. Okay, now I'll move on to the third part of the research, which is about maintenance. And the central question here is that, okay, we have sensing technologies, we have large amount of data produced. Then how can large volumes of inspection data enable predictive maintenance? And we know that there are different types of maintenance strategies. We have reactive maintenance, which is usually when we do this, when we see a very pronounced damage or failure, but we know that this can lead to very high cost and also very high safety risks. We can also do maintenance in a more periodic way. So we do it with a fixed interval over time, for instance, but this can either, if we do it very frequently, then we have to, again, spend a lot of money. But if we do it with a large interval, we may suffer from higher safety risk. That's where predictive maintenance can further improve on that. So predictive maintenance enables us to detect an early stage defect and also to make a prediction of how it will evolve over time or over loadings, for example. If we can detect the early defect, but it's not necessary to handle it right now, and if we predict that it we can still continue our operation for weeks or 1 month or something, then we can better plan our maintenance. We can even collect the maintenance of this defect with some other defects we identified. So this really makes maintenance much more proactive and much more well-planned. And how to do that? If we look at our train track system, it is well known that a lot of degradation in the vehicle track system will actually affect the vehicle track interaction. And then the poor vehicle track interaction will further accelerate the degradation of the components or even induce new degradation modes. And we can get information from the inspection technologies about the condition of the assets, and then we can do maintenance to try to improve their condition. And the link between these two is actually through degradation modeling and decision-making of the maintenance. We need to understand how degradation evolves, and we also need a automated or intelligent way to decide when to intervene and what type of maintenance actions to take. So here I would take train wheels, especially high-speed train wheels, as an example. We know that wheel actually has multiple degradation mechanisms, including the wear of the tread, wear of the flange, out of roundness, and also the development of the RCF defects, rolling contact fatigue defects. So these defects can directly affect the vehicle-track interaction. For example, it can give rise to the risk of having hunting behaviors. It can give rise to impact loading or increase the vibration or noise. And to obtain the condition of the wheels, there are a couple of inspection and measurement technologies available, both from the track side or wayside or in the depot. In this case study, we work on this maintenance research using data set from high-speed trains in China. And then based on this inspection data, degradation models can be built, which can further support decision-making so that we can know when and how we reprofile or turn the wheel and when to replace the wheel set. And so actually degradation modeling plays a very important role in this entire framework. And for train wheels especially, while we considering each individual degradation mode over time or over miles, we're also trying to find the coupling or correlation between different degradation mechanisms. For example, we find the wheel size can actually affect wear, rolling contact fatigue, and out of roundness at the same time. And now it is also well known that the wear and rolling contact fatigue, they are sort of competing with each other at the same stage. And there's also a strong correlation between out of roundness and rolling contact fatigue development. So by taking all these factors into account, we are not dealing with just isolated degradation processes, but within a coupled framework. On top of that, we also trying to consider other influencing factors, especially those coming from the operating conditions. For example, we found that seasonal effect actually is very significant for high-speed trains that was in operation. We observed more defects in summer than in winter in the data set. Another interesting factor that can be taken into account is the historical condition of the wheels. We found that the wheels that have previously developed defects are more likely to redevelop defects again. And among all these factors, there's one thing that can particularly highlight the importance of the vehicle-track interaction, that is the operating route. A high-speed train can operate over a wide range of routes, and we found that sections in different regions of the country will make different contributions to the development of the wheel damage. And for example, here we found that the lines in the south part of the country have much higher contributions. So this suggests that the environmental or climate factors may play a role here. And by knowing which routes a wheel used to operate on, along with other factors like the seasons or historical conditions, we can make better predictions instead of just using the time or miles. So based on all these considerations, analysis, modeling, we develop degradation models. And these models are able to predict first the risk of the defects. So those that we predict to have a higher risk, they truly exhibit higher damage rates in operation. And further on that, we can estimate the remaining useful life of the train wheels and the associated life cycle cost. And this predictability, the prediction capability makes it possible to even to further optimize the decisions of the maintenance. So now this model works like a sort of like a digital twin. So we get information from the inspection and then we make prediction. Then we try to produce some suggestions to help the decision making of the asset. And building on this network, this framework, we achieved predictive maintenance across different levels. So at the train set level, we can optimize the overhaul limit and the reprofiling interval for each individual train set. In this case, not every train will be maintained or be repaired with the same strategy. So each one has its own individual strategy. And for the wheel set level, we also have reprofiling strategy for each individual wheel set. So this strategy is also produced based on all its historical conditions, its prediction, and its life cycle costs. And we have implemented this framework and developed a software system that is now deployed and applied to more than 1,000 high-speed trains in China. And it enables daily updates and automated delivery of maintenance plans. And it also helps reduce damage rates. And at the same time, it saves maintenance costs. So we achieve improved safety and reduced cost at the same time. Okay, to conclude all the work I've presented, so we have the trainable LDV technology that is able to directly and contactlessly measure track vibration from operational trains. And the analysis of vibration data from both the train and also the track vibration provides continuous and quantitative assessment of track dynamic properties. And in the maintenance part, by trying to bridging inspection data and maintenance through degradation modeling and prediction, we are able to do predictive maintenance more effectively. I hope through presenting my past research, I demonstrate the motivation and also the value of doing research that connected inspection with assessment and further waste maintenance. And this has been and will continue to be the key research direction that I will be taking. And it is also a research domain that is so interdisciplinary, that is where a lot of collaborations can be expected. Knowledge from different fields or different topics are integrated to enhance the safety and the reliability of the railroads. And I believe with the increasing need for effective inspection and maintenance solutions, as well as with the rapid development of sensing technologies, AI, I believe there are exciting opportunities ahead in this direction. And last but not least, I want to thank all my advisors, co-authors, colleagues, both from TU Delft and Southwest Jiangsu University for their great support, contribution to the work, and I truly appreciate and enjoy the moment we spent together. In particular, I'm proud of many field measurement campaigns we did together. And I would like to also thank all the founding organizations and project partners for their support. Okay, finally, I'd like also to extend my gratitude to Realtek again for organizing this seminar. And looking ahead, I'm very, very excited to join University of Illinois and to start my faculty career in railway engineering. And thank you very much for your attention. And please feel free to reach out to me if you would like to have any follow-up discussion. And now I would be happy to take any questions you may have. Thank you.
Well, thank you, Yuanchen. Outstanding presentation, as we expected.
Thank you.
So to the audience, we do have time for some questions. And as I mentioned at the beginning of the presentation, please use the Q&A box, the Q&A feature of the Zoom application to submit your questions. And not the chat, but the Q&A. And we do have a couple of questions already. So I'll read the first one.
Yeah, thank you, Chris.
Where do you see the regulator, that is the Federal Railroad Administration here in the United States, and/or the investigative agency, the NTSB, in the system of non-intrusive and predictive maintenance? What are your thoughts about the role of the regulator or the NTSB on this sort of thing?
Yeah, I think that's a great question. I think it is first, I would say it is very important to always include the stakeholders, including the regulators and also investigation agency, when in the research design, in the research execution, and also in the application or the further deployment. So that's especially when it comes to railroad research, I would say. So if we do not have this in the picture, we will probably develop something that is not fully aligned with what is needed and what is expected. I probably could take an example of in Europe, like we have also regulators here, and the inspection technology definitely plays a big role in the safety, in the cost saving, but safety definitely plays a bigger role. And the regulators, they can help the standardization of the inspection technology. They can make it possible and make it the standard tools for all the railroads to follow. So that it is important when we develop a certain inspection technologies, we need to picture it in the context of the existing technology and what is missing and what is needed. And then we communicate actively and frequently with the regulators to make sure that our research and development is fully aligned with what is needed and and also with the and to really prove that there's added value for the existing regulation or investigation. I believe this non-intrusive inspection and also predictive maintenance, both from my past research and also the research I'll be taking in the future, will play a big role, and also can also benefit regulated and investigation agencies.
Okay, thanks. And I'll actually add a couple of comments myself to this, because one of the challenges we've faced in the United States is that regulations may have been written sometime in the past reflecting what the state of the art of the technology at that time was. As technology advances, those now somewhat antiquated regulatory language may interfere with or inhibit the development of new, more effective technologies to achieve the same end and actually do it more effectively than the old regulation might have required. And so that, I think, speaks to both the regulator and the NTSB, because the regulator, needs to be more open to how they can most effectively fulfill the safety mission by the flexibility in how they approach regulations, and NTSB can make such recommendations. One of the things that NTSB does is make recommendations to the FRA about their regulations and other policies. So,
yeah, that's a great remark, Chris. I think that's also just like the European efforts. We have this very big European project that actually bringing these regulators and also these stakeholders in the same project, so they were well connected. So, and we are always aligning each other on the direction we're going to take for future research and also for future regulation. I think that you really make a great point, Chris.
Thank you. Next question. How does the cost of the system compare with ease of use? And can the data collection, post-processing output easily integrate with existing asset management systems, such as off-the-shelf ones, or be ported into legacy systems via APIs or other means? And what about the role of AI tools for reporting and decision making? So there's a lot of points there. I don't know if you can you also see the questions in case?
Okay, let me try to.
Just so you don't remember everything I said, which was a lot to that question. So,
okay, I think so. That's a great series of questions, but I don't think I have a lot of time, but I will be short in trying to get something here. I see about first the cost compared to the ease of use. Okay, I think the cost is not directly made to compare with the ease of use. I think there are like two matrices when we try to assess the usability of the system. The cost has to be assessed, I would say, also considering the benefits. So it's not purely the cost itself that matters, it's what you gain by investing, both the research and also the future deployment. And the ease of use, I think that's a great point. It's actually also connected with the previous question about regulation, or basically the users or the end users or the intermediate users, how interpretable your method is or how actionable the output is. I think that's also one of the efforts we're trying to make the analysis more interpretable and more actionable. This actually links to maybe the question about AI part. So we use some of the AI method, as mentioned in the presentation, but not everywhere. The reason is that we want to keep also this interpretability and this interpretability is, I think, all the practicality. So I know AI works in a lot of domains, a lot of applications, but sometimes you have to compromise your interpretability. And this is something not we always want, especially when it comes to railroad asset management. We want to know in a prescriptive way what could happen and how we can do it with a more interpretable way. We have also, the combination or integration with the existing system. I think that's great. That's exactly why we develop all this system or these technologies. We're not trying to replace the existing technologies. We try to measure something that is complementary, that is something can be added on existing either regulations or existing the applied technology so that we can get more information, more insights. We know the structure better so that we can make prediction better. I think they are definitely complementary. This is complementariness at the beginning of the research design. I think I answered most of the part of the question, Chris.
Okay, thank you. Next question, can you please briefly explain how LDV works again?
Hey.
And if you need to go back to a slide, yeah, whatever.
Yeah, so I'll be very brief, actually. So I hope by this analogy, it helps a little bit, but maybe still it's kind of an abstract concept because basically the laser is just a light. Then you may wonder, how do you get vibration information from a piece of light? This is actually works based on the Doppler frequency. So we have a light that is shooting on a moving target with a frequency f, and then the light will be reflected or scattered back to the LDV device. And when LDV here, as the receiver, it measures this wave, the frequency will be no longer the same as the original frequency it emitted. It will have a shift. And this shift follows Doppler effect. And this shift is proportional to the movement of the target or the object. So this is really where the magic takes place. So we measure the speed not directly by measuring how much displacement it has, but we measure this frequency shift. So this is essentially how LDV works, to use light to measure vibrations. I think the audience are definitely welcome to approach me, drop me an email if you want more clarification or discussion about this working principle.
Okay, thank you. Next slide compliments you on the presentation. Great presentation, thank you. Are you able to associate the vibration recorded to specific track deficiencies, or the LDV would only localize problematic zones and then further investigation is needed? So I think he's getting at the granularity of what you're identifying with the LDV.
Yeah, that's a very great question. I think what we have done so far, we can already kind of distinguish whether if the problem comes from the rail or the surface of the rail, or it comes from further below the rail, like the track support from the ballast. So that's already a step that can already provide some distinguishable information or insights. But definitely we're not satisfied with this. So that's why we're also working on this load response relationship estimation. Because we know from the track dynamics or structure dynamics, we know at different frequencies, different components, or let's say different stiffness or different damping play different roles at different frequencies. So in the other way, we have this whole frequency response. Let me get that slide also to help a little bit better for the explanation. Yeah, this one. So we get this whole transfer function over the entire frequency. And we know at different frequencies which mechanism play a role, and they may indicate something associated with that particular track components or stiffness or damping. So this is where we believe we can reach even better understanding. So preferably we can pinpoint where the problem is, and even the severity of the problem, and perhaps further link this one to the maintenance decision. So that's definitely is the goal. I think we are making progress, but there are also a lot of research that is ongoing and will be achieved in the future, I think.
Okay, thank you. Next question, also related to LDV. This LDV technology seems only for vertical vibration measurement. How about track panel lateral vibration?
Yeah, that's also a great question. So I think it is 100% correct that currently our setup can only measure vertical, which already produces a lot of data, a lot of information, something we have already achieved great progress, but there are also a lot more to do. So it's definitely would be interesting to measure the lateral or maybe even other directions. But for now, we haven't really achieve that at the moment. But that's indeed within the scope of our research interest. And we believe that we first start with vertical, and with all the experience or the insights we gain from the existing research will be very helpful and beneficial when we look at other dimensions. So we do it like step by step, and we don't do all direction at the same time, at least for now.
But there's no technical reason why you can't do it. I think it's just a
Yeah.
matter of getting the laser,
Yeah, the
having
setup
access
would
inside,
be,
let's say.
yeah, that's true. So the setup would be more challenging to design and to implement for sure. So, but there are also solutions where we are trying to brainstorming for now.
Okay, thank you. So the next question is about managing the vast quantity of data that's being generated. Are you talking about using machine learning, artificial intelligence, or other related ways to manage these conditions?
Yeah. So we are indeed. So we actually combine both this like a machine learning method or data-driven method with also conventionally like handcrafted feature or thresholding. So it's a combination. And we try to use of AI in this because the data set we have is not just large, but also it has great variety. As you can imagine, we measure hundreds of kilometers per day. The train travels across the entire country. So there's a huge variety. Also the train speed is different. Everything's different. So the variety is something that is not easy to handle by manually engineered features. So it's difficult to generalize when we use traditional way, but we believe AI is pretty good at it. It can learn features that is maybe even beyond what we can program directly using our experience. So we are using AI for that part already. And we believe there are also opportunities to use AI for more later stage detection or assessment. But for now, we rely more on the more interpretable way, which is actually one of the benefits we believe that is needed to make the analysis and assessment results more interpretable to researchers, but also to end users.
Okay, thank you. We'll just we're almost done with the questions. I don't want to take up too much more of your time.
No problem.
So what was the cost of the predictive maintenance regime for wheel reprofiling relative to the original maintenance regime?
Yeah, that's a very great point. I wouldn't give you the numbers, but I can tell you that the reprofiling of the wheel takes more material than the wear itself. Because the wheel certainly have a lifespan, the wheel cannot be very small. And it is actually reprofiling that takes a lot of materials off. It's not the wear, it's not the operation. And we are now optimize this reprofiling process in a way that we reprofile only when it is needed. And we only reprofile to the target profile that we believe it is sufficient for the rest of the lifespan. So by doing this, we reduce the total number of reprofiling, we reduce the depth of reprofiling per time. And this saves a lot of cost in the material of the wheel, and in the end, we extend the lifespan of the wheel. so we don't have to buy a lot of new wheels to replace the old wheels. So this really saves a lot of money for the train operators.
Okay, thank you. Next question. First of all, thanking you for your presentation. And actually, if you go back to slide 30, so just 3 slides back.
Yeah. Yes.
So this gentleman's asking, how did you align the multi-year inspection data and the left-right track position, especially considering maintenance work between inspections?
Yeah. So the alignment is actually, if I go back to 2 slides before, or maybe no, it's after. Okay, I'll skip that. So the alignment is based on all our multi-signal fusion methods. So we have the GPS that record the train location and speed. We have also the video camera that actually record the trajectory of the laser support. So these are the information that is essential to align them to the accuracy of each cross tie or each sleeper. So this is how we align multiple measurements for the onboard measurement we did. And I guess you probably also want to know the alignment with the track geometry measurement. I think that is also, that's not because we don't do geometry measurement by ourselves. So what we get is the geometry data. And for the alignment, then we cannot guarantee a full accuracy of an individual cross tie, but we believe the general pattern that seems to be very repeatable, that is an indicator that the alignment is not bad. And we don't really see directly changes in track geometry over the years, which we believe there is no big maintenance activities between this period of analysis. But definitely, if there is, we should be able to see it both from the track geometry measurement and also the onboard measurement we have been doing. But we don't see it in none of them. So we believe maintenance was probably not happening during the measurement period.
Okay, thank you.
Yeah.
2 more questions. One is, this individual is asking, are they correct that the method you're presenting is focusing on track geometry failure modes? Is there a potential to address rail surface defect or internal defects?
Okay. It is not directly designed for handling track geometry failure modes, I would say. It is certainly kind of correlated with the assessment based on geometry. That is yes, because geometry also reflects the track conditions. But we are not directly measuring geometry. We are measuring actually the response of the train and track systems in just normal operation and also their interaction. So, and we believe this vibration information can provide earlier stage detection than geometry. That's why we want to develop this technology. We want to make it useful. I think for rail surface defect, that is yes, and that's, I believe this LDV technology is not the only technology that is able to detect a rail surface defect. There are many other technologies that is capable for that. But for internal defect, that will be much more challenging, I think, from my experience. I wouldn't say no, because maybe there can be some vibration feature that is sensitive to some internal defect, but that is not directly within the scope of my past research.
Okay, thank you. The one last question that's somewhat related, or at least partly, how does RCF, rolling contact fatigue, affect your test results? And another aspect of that is there any signal noise from automatic train control signaling that might interfere or affect with this? There's sort of 2 parts to the question. One is RCF and the other one's automatic train control signal.
Yeah, I think the part with the RCF is an interesting one. So we can actually detect rail surface defects, which can include some of the RCF patterns like squats. And what is more interesting to know is that sometimes there is a correlation between rail surface defect development with other degradation of the track structure, like the support condition, the stiffness or damping changes. Sometimes it is one that's contributed to the other. Sometimes it is the other way around. Sometimes they co-develop. And this is where the technology becomes very useful, because we sort of, by measuring both train and track vibrations, we can try to understand how they correlate with each other. So this is, yes, for RCF, but we believe we can also get better understanding than just detect the RCF. Maybe we can correlate it with something happening even below the rail. And for the positive train control, because I think that that means some current in the rail or something, I guess, or it is some electromagnetic wave that is propagating in the air. But
Yeah.
at least from my experience, we don't have this interference, because the interference of the LDV measurement mainly comes from the light, the laser. So that's why with the speckle noise, because of the surface, is a big problem. That's why we developed a solution to that. But we didn't experience this electromagnetic interference.
Yeah, now that I think about it, I don't think this would be PTC. Automatic train control typically has an electromagnetic wave in the rail, depending upon the status of tracks ahead. So I think it's whatever the electromagnetic field emanating from the rail is. I'm guessing that that's not going to be a factor for your work, but
Yeah, because the laser has a fixed wavelength and also more or less at a certain order of the frequency. So it can be kind of robust by concentrating only to that regime.
okay.
Yeah.
Well, that's the last of the question. Again, a number of people thank you for a very interesting presentation, and I certainly want to join them and say it's fantastic to hear from you, hear about your research, what its implications are for the future of rail transportation, safety, and efficiency, not only in North America, but worldwide. And I'm looking forward to you joining us later this year. So
Thank you. Thank you, Chris. Thank you, everyone that attended the session and also posed all the amazing questions. Thank you very much.
yeah. Right. Well, have a very nice evening, and and some people asked the question about the availability of your slides. Will it be all right for us to post the PDF on our webpage?
Yeah,
Okay. All right.
definitely. I will send it to Chrissy later today.
Okay, great. Well, again, thank you very much. You have a nice evening, and we'll be in touch. And thanks,
Yeah,
everybody.
thank you.
Thank you, everybody, for joining us. Bye-bye.
Bye.